Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the day behind you settle into memory, to allow yourself this time. Where in the world are you watching from? A quiet bedroom where the world outside has finally gone still? A cozy corner where you've carved out space just for yourself? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something that shouldn't exist, a region of space so vast and so empty that when astronomers first discovered it, they thought their instruments had failed. We're going to drift through the Boötes Void, a supervoid in space nearly 330 million light-years across, a bubble of almost perfect darkness in the cosmic web. We'll discover how something this enormous managed to hide in plain sight, understand what its existence tells us about the universe itself, and contemplate what it means to find emptiness on a scale that defies human comprehension. But don't worry, this isn't going to be a journey into cosmic horror or existential dread. Instead, we'll move slowly and carefully through the science, the discovery, and the meaning of this void, taking our time with each revelation. We'll treat this emptiness not as something frightening, but as something remarkable, a puzzle the universe has left for us to slowly piece together. By the end, I think you'll find that even the darkest, emptiest places in the cosmos have their own kind of beauty. If you enjoy these calm explorations of the universe, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with your nights, for choosing to learn as you drift towards sleep. So settle in. Let your shoulders drop away from your ears. Take a slow breath and let it out even more slowly. And let's begin our slow drift through the largest empty space humanity has ever found. There's nowhere you need to be right now. Nothing you need to do. Just listen and let the story of the void unfold. Let's explore the darkness together. When you look up at the night sky, what you're seeing is deceptive. The stars scattered across the darkness appear random, as though someone took a handful of luminous sand and scattered it across black velvet. For most of human history, we believed this randomness was real, that the universe had no structure beyond the patterns we imposed upon it through our constellations. We were wrong in the most beautiful way possible. The universe isn't random at all. If you could step far enough back, if you could see the cosmos from a distance of billions of light years, you'd discover that galaxies arrange themselves in patterns. They cluster together in groups. Those groups join into superclusters, and those superclusters trace out filaments, vast cosmic threads that stretch across hundreds of millions of light years. Between these bright filaments lie voids, regions where galaxies are rare or absent entirely. This structure, called the cosmic web, is one of the largest scale patterns in the universe, a sculpture shaped by gravity over billions of years. Think of it like a sponge, if a sponge were made of galaxies and dark matter instead of cellulose. The solid parts of the sponge are the filaments, dense with galaxies and matter. The holes in the sponge are the voids, regions where matter is scarce. Most voids are perhaps 50 to 100 million light-years across, substantial but not extraordinary. They're simply the spaces between the bright threads of the cosmic web, the negative space that gives the structure its shape. But in 1977, an astronomer named Robert Kirshner and his colleagues were mapping galaxies in the constellation Boötes, a region of sky in the northern hemisphere. They were conducting a redshift survey, measuring how fast galaxies were moving away from us, which tells us how distant they are. It was painstaking work, the kind that required patience and precision. They expected to find galaxies scattered more or less evenly across their survey area, perhaps a bit clumpy, but following the general pattern they'd seen elsewhere in the universe. Instead, they found almost nothing. In a region of sky where they should have detected perhaps 2,000 galaxies, they found about 60. The numbers were so strange that they initially assumed something had gone wrong with their observations or their instruments. but the data held up under scrutiny. They had stumbled upon a void far larger than any previously known, a bubble of darkness in the cosmic web so vast that it seemed to violate the expected structure of the universe itself. This was the Boötes Void, sometimes called the Great Nothing, a region of space approximately 330 million light-years in diameter, where galaxies are extraordinarily rare. To put that scale in perspective, our entire Milky Way galaxy is only about 100,000 light-years across. The Boötes Void is 3,300 times wider than our entire galaxy. If our galaxy were the size of a coin, the Boötes Void would be a sphere roughly the size of a small city, and yet, for all its enormousness, it had remained unnoticed until the late 1970s, hidden in plain sight among the stars. And this discovery raises a question that will carry us through our entire journey tonight. A question both simple and profound. How does something this large, this empty, come to exist in a universe that's supposed to be expanding uniformly in all directions? The answer, as we'll discover, tells us something fundamental about the universe itself. The human mind struggles with cosmic distances. We evolved to understand the space between trees in a forest, the distance across a valley, perhaps the journey from one settlement to another. We can imagine 1,000 kilometers, maybe even visualize the curve of the Earth. But 330 million light years, that number is so large it becomes abstract, almost meaningless. And yet astronomers measure such distances with remarkable precision. Away from you, the wavelengths of that away from you, the wavelengths of that light stretch out, shifting toward the red end of the spectrum. This is the same principle that makes an ambulance siren sound lower pitched as it drives away from you, except applied to light instead of sound. The faster something moves away, the more its light shifts toward red. Because the universe is expanding, distant galaxies are moving away from us, and the farther away they are, the faster they recede. This relationship, discovered by Edwin Hubble in the 1920s, means we can measure how much a galaxy's light has redshifted and calculate its distance from us. It's an elegant method, turning the expansion of the universe itself into a cosmic measuring tape. When Kirshner's team measured redshifts in the Boötes region, they found galaxies at certain distances, then a huge gap where almost no galaxies appeared, then galaxies again at greater distances. It was as though they were looking at the near side of a bubble through its nearly empty interior and out to the far side. By mapping the three-dimensional positions of these galaxies, they could trace the boundaries of the void itself. The void isn't perfectly empty, of course. Those 60 or so galaxies they did find are scattered within its volume, lonely islands in an ocean of darkness. But the density of galaxies inside the void is only about 10% of what it should be if matter were distributed evenly. Imagine a city where 9 out of every 10 buildings simply don't exist, where vast stretches of empty lots separate the few structures that remain. That's the Boötes Void, a cosmic ghost town on an unimaginable scale. Later observations refine these measurements. Astronomers use more powerful telescopes, more sensitive instruments, and more sophisticated techniques. They confirmed that the void is roughly spherical, extending from about 700 million light-years away from us to more than 1 billion light-years distant. Its centre, the point of maximum emptiness, lies approximately 790 million light-years from Earth, in the direction of the constellation Boötes. But measuring the void's size was only the beginning. The harder questions were just starting to emerge. Why is this region so empty? What happened to the matter that should be there? And perhaps most intriguingly, is the Boötes Void unique? Or are there other such enormous empty regions lurking undiscovered in the cosmos? These questions would take decades to answer, and the answers, when they came, would reshape our understanding of how structure forms in the universe. Let that image settle in your mind for a moment. This vast sphere of darkness, larger than anything humans had previously conceived, waiting patiently in the night sky for someone to notice its absence. And that very patience, that capacity to hide while being so enormous, leads us to consider how we even know what we're looking at when we peer into such depths of space. There's something dreamlike about astronomical observation that we don't often acknowledge. When you look at a distant galaxy, you're not seeing it as it is now. You're seeing it as it was when the light you're detecting left its stars, perhaps millions or even billions of years ago. The galaxy you observe might have changed dramatically in the time it took that light to reach you. It might have collided with another galaxy, might have formed new clusters of stars, might look entirely different if you could somehow see it in its present state. The light from the galaxies surrounding the Boötes Void began its journey toward Earth roughly 700 million to 1 billion years ago. To put that in terrestrial terms, when some of that light started travelling toward us, Earth was in the midst of the Cryogenian period, a time when our planet experienced its most severe ice ages, possibly frozen from pole to pole. There were no plants on land, no animals with backbones. Life was still confined to the oceans, simple and strange. That light travelled through expanding space for all that time, crossing distances that would have been slightly shorter when it began its journey, because the universe was smaller then. It passed through clouds of gas and dust, through the gravitational fields of countless stars, perhaps even through the dark matter halos of unseen galactic masses. And all the while, it was redshifting, its wavelength stretching as space itself expanded around it. When that ancient light finally reaches our telescopes, it carries information encoded in its spectrum, the rainbow of colours and dark lines that tell us what elements exist in those distant galaxies and how fast they're moving. By analysing this spectrum, astronomers can determine the galaxy's composition, its velocity, its age, and its distance. Each photon that enters our detectors is a messenger from deep time, a traveller that has crossed an expanse of space so vast that human language barely has words adequate to describe it. The galaxies on the near side of the Boötes Void are roughly 700 million light-years away. Those on the far side are perhaps 1 billion light-years distant. This means the void itself is about 300 million light-years thick in our direction of view. But here's where it gets strange to contemplate. We're not seeing the void as it is now. We're seeing it as it was hundreds of millions of years ago, frozen in time like an ancient photograph. What does the void look like today, in its present state that we cannot observe? Has it changed? Have new galaxies formed in its depths? Has it expanded further, or has gravity begun to draw matter back into it? We can make educated guesses based on our understanding of cosmic evolution, but we cannot know with certainty. The present state of the void is hidden from us behind an uncrossable barrier of time and distance. This is one of the strange beauties of astronomy. We study the past, not because we choose to, but because we must. The universe's size mandates that we are archaeologists of light, examining ancient signals to understand processes that happened when Earth itself was unrecognisably different. And yet from these ancient signals, we can reconstruct the history of the cosmos with remarkable accuracy, piecing together how structures form and evolve over billions of years. Which brings us to a question that occupied astronomers for years after the void's discovery. If we're looking at the void as it was hundreds of millions of years ago, how did it get so empty in the first place? To answer that, we need to go back much further in time, to the very beginning of structure in the universe. In the beginning, there was smoothness. When the universe was about 380,000 years old, it was filled with a nearly uniform soup of hydrogen, helium, and radiation. The temperature had finally dropped enough for electrons to combine with atomic nuclei, allowing light to travel freely through space for the first time. This light, stretched and cooled by billions of years of expansion, is what we now observe as the cosmic microwave background radiation, the afterglow of the Big Bang. But that smoothness was not perfect. There were tiny fluctuations in density. regions where matter was just slightly more concentrated than average, and regions where it was just slightly less concentrated. These fluctuations were small, differences of only about 1 part in 100,000, like ripples on an otherwise perfectly still pond. They were the quantum fluctuations from the earliest moments of the universe. Stretched to cosmic scales by the brief period of rapid expansion called inflation, those tiny differences in density were the seeds from which all structure in the universe would grow. In regions that were slightly denser than average, gravity had slightly more material to work with. It began to draw in surrounding matter, making these regions denser still. In regions that were slightly less dense than average, matter was drawn away toward the denser regions, making the underdense areas even emptier. This process is called gravitational instability, and it's the fundamental mechanism by which structure forms in an expanding universe. Over millions of years, these tiny density differences grew. The denser regions pulled in more and more matter, forming the first stars and galaxies. These galaxies clustered together along lines determined by the distribution of dark matter, the invisible substance that makes up most of the universe's mass. The dark matter formed a gravitational scaffold, and ordinary matter fell into that scaffold like water flowing into river valleys. The regions that started out less dense became voids, not because matter was actively removed from them, but because gravity pulled whatever matter was there toward the denser regions nearby. It's similar to what happens when you have hills and valleys. Rain that falls on the hills flows down into the valleys. The hills don't become drier because something removes the water. They become drier because gravity draws the water away to lower elevations. The Boötes Void began as a region with a slightly lower than average density in the early universe. Over hundreds of millions of years, as structure formed and galaxies clustered along filaments, the matter in this region was drawn toward the surrounding denser areas. The few galaxies that did form within the void were those rare places where local density fluctuations were just barely strong enough to overcome the overall underdensity of the region. Computer simulations of structure formation run in the late 20th and early 21st centuries showed that this process naturally produces voids of various sizes. The cosmic web structure, with its filaments and voids, emerges inevitably from the initial conditions of the universe, plus the laws of gravity and the expansion of space. You don't need any special mechanism or unusual physics to create voids. They're simply the inverse of the clustering process, the spaces left behind when matter flows toward concentrations. What makes the Boötes Void unusual is not that it exists, but that it's so large. Most voids are smaller, 50 to 100 million light-years across. The Boötes Void is roughly 3 times that size, pushing at the upper limits of what standard cosmological models predict should exist. It's rare but not impossible, like a particularly large bubble in boiling water. It tells us that the early universe's density fluctuations, while typically small, occasionally created regions with significant underdensities, and those regions evolved into supervoids like Boötes. And this brings us to something worth pondering as you settle deeper into rest. The emptiness we're exploring tonight isn't really empty. It's shaped emptiness, structured absence, darkness that exists in a particular form because of events that happened when the universe was unimaginably young. The void is as much a part of the cosmic web as the bright filaments of galaxies. It's the silence between the notes that gives the music its form. By the 1990s and early 2000s, astronomers had mapped enough of the sky to see the cosmic web in 3 dimensions. Projects like the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey measured distances to hundreds of thousands of galaxies, creating 3-dimensional maps of the universe's large-scale structure. When these maps were visualized, the cosmic web appeared in stunning clarity. Imagine a 3-dimensional lattice made of light, with galaxies strung along threads that connect nodes of high density. The threads are the filaments. Vast structures hundreds of millions of light-years long where galaxies cluster closely together. The nodes are the superclusters, massive concentrations of thousands of galaxies, and between the threads, defining their shape by their absence, are the voids. The Boötes Void appeared in these maps as a particularly large bubble in this cosmic foam. Surrounding it were dense regions like the Boötes supercluster, sheets and filaments of galaxies that form the void's walls. The contrast was striking. In the dense regions, you might find dozens of galaxies in a volume of space just a few tens of millions of light years across. In the void's interior, that same volume might contain no galaxies at all. These maps also revealed that the Boötes Void wasn't alone. Other large voids existed throughout the surveyed regions of space. There was the Sculptor Void, the Canes Venatici Void, the Eridanus Supervoid, and many others. Some were comparable in size to Boötes, others were smaller. Together they made up a significant fraction of the universe's volume. If you calculated the total volume of all the voids versus the total volume of all the filaments and superclusters, you'd find that voids occupy the majority of space. The universe is, in a sense, mostly empty. But that emptiness is deceiving because the voids, while low in normal matter, are not devoid of dark matter. Simulations suggest that dark matter, though less concentrated in voids than in filaments, still forms a diffuse web within the void regions. This dark matter, invisible to our telescopes, provides the gravitational framework that shapes how the small amount of normal matter in voids behaves. The few galaxies that do exist within the Boötes Void are interesting in their own right. They tend to be smaller and dimmer than average, often dwarf galaxies with low rates of star formation. They're lonely objects separated from their nearest neighbours by vast gulfs of space. While a typical galaxy in a dense region might have dozens of neighbours within a few million light years, a galaxy in the Boötes Void might have to travel 50 million light years or more to reach its nearest companion. This isolation affects how these void galaxies evolve. Galaxies grow partly by merging with other galaxies, by accreting gas from their surroundings, by having their star formation triggered by interactions with neighbours. In the void, these processes are rare. The void galaxies lead quiet lives, slowly consuming whatever gas they have, forming stars at a leisurely pace and evolving without the dramatic interactions that shape their cousins in denser environments. Astronomers have studied these void galaxies with great interest because they represent a sort of control group in the experiment of galaxy evolution. By comparing them to galaxies in average or dense environments, we can learn how much of a galaxy's properties are intrinsic and how much are shaped by its surroundings. It's like studying people who grow up in isolated villages versus crowded cities and seeing how the environment influences development. And as our three-dimensional maps of the universe grew more detailed and covered larger volumes of space, a profound realization emerged. The cosmic web, with all its filaments and voids, is not random. It follows patterns that can be predicted from the initial conditions of the universe. It's a structure that emerged naturally from the interplay of gravity, dark matter, dark energy, and the expansion of space. The Boötes Void, vast and empty as it is a predictable consequence of how the universe organises itself on the larger scales, which leads us gently toward understanding not just the void itself, but what it tells us about the fundamental nature of reality. To understand the Boötes Void, we must understand something we cannot see, something that makes up roughly 85% of the matter in the universe, but has never been directly detected. Dark matter is one of the great mysteries of modern physics, a substance whose existence we infer from its gravitational effects, but whose nature remains unknown. We know dark matter exists because of how galaxies rotate. When astronomers measure the speed at which stars orbit the centres of galaxies, they find something strange. Stars far from the galactic centre are moving much faster than they should be if the only matter present were the stars and gas we can see. According to the laws of gravity, these outer stars should be moving more slowly, just as planets farther from the Sun orbit more slowly than planets closer in. but they're not. They're moving as if there's much more mass in the galaxy than we can detect with our telescopes. This invisible mass is dark matter, and it doesn't just exist in galaxies. It forms vast halos around them, extending far beyond the visible edges of the galaxies themselves. On even larger scales, dark matter forms the filaments of the cosmic web, the gravitational framework onto which ordinary matter collapses. It's the skeleton of the universe, invisible but fundamental to everything we see. In the regions that would become voids, dark matter was initially present but less concentrated than in areas that would become filaments. A structure formed. The dark matter in these underdense regions fell toward the surrounding overdense regions, following gravity's inexorable pull. But because dark matter doesn't interact with light or normal matter except through gravity, it doesn't form concentrated objects like stars or planets. It remains diffuse, spread out across vast distances. Computer simulations of structure formation include dark matter as a critical component. When astronomers run these simulations, starting from the tiny density fluctuations in the early universe and evolving them forward according to known physics, they see the cosmic web emerge naturally. Dark matter clumps into filaments and nodes. Ordinary matter falls into these dark matter concentrations and forms galaxies. The spaces between the filaments become voids. These simulations predict that even within voids, there should be some dark matter present, just at much lower density than in filaments. This dark matter forms thin strands and small clumps within the void, too diffuse to attract much ordinary matter, but still present as a faint gravitational web. We cannot see this web directly, but its effects can be detected through careful observations of how light from distant objects bends as it passes through the void's gravitational field. The distribution of dark matter in and around the Boötes Void shapes how the void has evolved over time. The dark matter in the void's walls attracts matter toward those walls, pulling galaxies and gas out of the void's interior. The dark matter within the void itself is too diffuse to form significant structures, but provides a subtle gravitational landscape that influences the few galaxies that do form there. One of the beautiful aspects of dark matter's role in the void is how it demonstrates the importance of initial conditions. The reason the Boötes region became a void rather than a filament comes down to how dark matter was distributed there in the early universe. A slightly different distribution, and this region might have become a supercluster instead. The entire structure of the universe, in a sense, was encoded in the distribution of dark matter moments after the Big Bang. And this raises a profound question that cosmologists continue to explore. What is dark matter? Is it a new kind of particle, something that exists beyond the standard model of particle physics? Is it a modification of gravity that we don't yet understand, or is it something even stranger, something that will require us to rethink our most basic assumptions about the universe? The answer, when it comes, will reshape our understanding not just of voids like Boötes, but of the fundamental nature of reality itself. Let that mystery rest in your mind as we turn our attention to the matter we can see. The Boötes Void is defined by absence, but that absence had to go somewhere. The matter that should be in the void, that 10% or so of galaxies that are missing, didn't simply vanish. It flowed out of the void region over hundreds of millions of years, drawn by gravity toward the denser regions that surrounded the growing emptiness. If we could trace the history of every atom that should be in the void, we'd see a slow, patient exodus. In the very early universe, before stars existed, this matter was in the form of hydrogen and helium gas. It was distributed more or less evenly across the region that would become the void, perhaps just slightly less dense than the cosmic average. As the universe expanded and cooled, and as the first stars began to form in denser regions, this gas felt the gravitational pull of those distant structures. Gas doesn't move quickly through space on its own. It's not like water flowing rapidly downhill. Instead, it drifts slowly, responding to pressure gradients and gravitational fields. Over millions of years, the gas in the void region gradually flowed toward the regions of higher density surrounding it. This process is called gravitationally driven flows, and it's one of the fundamental mechanisms by which structure forms in the universe. As the gas flowed out of the void, the density difference between the void and its surroundings grew larger. The denser regions became denser still, attracting even more matter. The void became emptier, having less matter to hold on to what remained. It's a positive feedback loop, an example of how small initial differences can grow into large-scale structure, given enough time and the right physical processes. Some of the gas that left the void region ended up in the walls of the void, the regions of higher density that form the void's boundary. There, it contributed to the formation of galaxies in those boundary regions. Other gas travelled farther, flowing along the cosmic web's filaments toward distant superclusters. In both cases, this matter became part of structures that we can now observe, galaxies and clusters that are denser and more active than they would be if the void's missing matter were still evenly distributed. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. The few galaxies that did form within the void tell us something important about this process. They exist in places where local density fluctuations were strong enough to hold on to gas despite the overall underdensity of the region. These local overdensities acted as small gravitational anchors, creating tiny islands of structure in the ocean of emptiness. But even these void galaxies are affected by their environment. They have less nearby gas to accrete, fewer opportunities to merge with neighbours, and lower rates of ongoing star formation. Many of them likely formed most of their stars early in the universe's history, when there was still enough local gas to fuel star formation, and have been slowly fading ever since. They're like small towns in a remote region that thrived briefly when they were founded, but have been declining slowly ever after as resources dwindled and people moved away. The timescale of this matter exodus is worth contemplating. It didn't happen suddenly. It wasn't a dramatic event, but a gradual process that unfolded over hundreds of millions of years, perhaps even billions. When the first atoms flowed out of what would become the Boötes Void, the universe was young, dominated by dark matter and simple gases. By the time the void had reached something like its current state, the universe had aged considerably, and complex structures like galaxies and galaxy clusters had formed throughout space. This long, slow process of matter migration is still happening today. The void continues to evolve, though at a much slower rate than in its early history. Gas continues to flow along the cosmic web's filaments. Galaxies continue to drift, their motion shaped by gravity's patient pull. The Boötes Void of today is not identical to the Boötes Void of 1 billion years ago, and it will be different still 1 billion years in the future. It's a dynamic structure, changing on timescales so vast that human civilization is but a flicker in comparison. Space is cold, but it's not uniformly cold. Different regions of the universe have different temperatures, and these temperature variations tell us about the physical processes occurring in those regions. The Boötes Void, despite its emptiness, has a temperature, and that temperature reveals something about the void's nature and history. The baseline temperature of the universe is about 2.7 degrees above absolute zero. The temperature of the cosmic microwave background radiation that fills all of space. This is the cooled remnant of the Big Bang's heat, stretched and diluted by nearly 14 billion years of expansion. But in regions where matter clusters together, where gas compresses and heats up, temperatures can be much higher. In galaxy clusters, where thousands of galaxies gather together in gravitationally bound systems, the space between galaxies is filled with hot gas, often heated to tens of millions of degrees. This gas shines in X-rays, invisible to our eyes but detectable by space telescopes. The heat comes from the gravitational energy released as matter falls into the cluster, like water heating up as it rushes over a waterfall. In voids, the opposite happens. The low density of matter means less gravitational compression, less heating from infall. The gas in voids, what little of it there is, remains cooler than the gas in filaments or clusters. Observations suggest that void regions are slightly cooler than the cosmic average, with the Boötes Void perhaps a few millionths of a degree cooler than you'd expect if matter were distributed evenly. This temperature difference is tiny, almost negligible, but it's detectable through its effect on the cosmic microwave background radiation. When this radiation passes through a region of hot gas, the photons gain energy through a process called the Sunyaev-Zeldovich effect, named after the Russian physicists who predicted it. When the radiation passes through a region of unusually cool or low-density gas, the effect is reversed, creating a cold spot. The Boötes Void creates such a cold spot. When the cosmic microwave background radiation passes through the void, it encounters less matter and cooler gas than average, and this leaves a subtle imprint on the radiation's temperature pattern. By measuring this imprint, astronomers can study the void's properties in a way that complements traditional galaxy surveys. There's something almost poetic about this. The void, defined by what it lacks, still makes itself known through its effect on ancient light from the universe's infancy. It's like a shadow that falls on a distant wall, revealing the shape of something unseen. The void cannot hide completely, even from light that has been travelling for nearly 14 billion years. But temperature tells us more than just the void's density. It also tells us about the void's history and evolution. If the void had been filled with large amounts of hot gas at some point, we'd see evidence of that in temperature maps and X-ray observations. We don't see such evidence, which confirms that the void has been relatively empty for most of cosmic history. The coolness of the void also affects how matter behaves within it. Cool gas is less likely to collapse and form new stars than hot gas that has cooled down and condensed. This may be one reason why the void galaxies have low star formation rates. They're working with cooler, less active gas that doesn't readily collapse into dense clouds where stars can form. As telescopes become more sensitive and temperature measurements more precise, astronomers continue to refine their understanding of void temperatures. Each new observation adds detail to our picture, helping us understand not just the Boötes Void, but voids in general, and how these empty regions fit into the larger story of cosmic structure formation. Let the coldness of the void settle into your awareness, not as something frightening, but as something natural, a place where the universe takes a breath between its more active regions. The void is a pause in the cosmic symphony, and pauses are as essential to music as the notes themselves. The universe is expanding, and it has been since the Big Bang. But that expansion isn't uniform on small scales. In regions where gravity is strong, where matter clusters together in galaxies and galaxy clusters, expansion is overcome by gravitational attraction. These regions don't expand. Instead, they're bound together, held static or even contracting slightly as matter falls inward. But in voids, where gravity's pull is weak because matter is scarce, expansion dominates. The space within a void expands more freely than the space in denser regions. This doesn't mean the void itself is growing faster than the rest of the universe exactly, but rather that the expansion of space is less resisted by gravity within the void's volume. Think of it this way. Imagine a landscape of hills and valleys, where the valleys are the voids and the hills are the dense regions. Rain falls evenly across this landscape, representing the expansion of space. In the valleys, the rain pools and spreads out freely. On the hills, the rain is held in place by the shape of the land, pooling in dips and crevices, flowing downhill but not spreading out as much. The void is like the valley, where expansion proceeds more naturally because there's less structure to resist it. This difference in expansion rates, though small, has observable consequences. Galaxies in voids tend to move away from each other faster than galaxies in average density regions, after accounting for the Hubble expansion. This is called the void expansion effect, and it's been measured in several large voids including Boötes. But there's a twist to this story, and it involves one of the great mysteries of modern cosmology: dark energy. Dark energy is the name we give to whatever force is causing the universe's expansion to accelerate. Observations show that not only is the universe expanding, but that expansion is speeding up over time. Galaxies are moving apart faster now than they were in the past, and they'll move apart even faster in the future. Dark energy appears to be a property of space itself, a kind of energy that fills the vacuum. The more space that exists, the more dark energy there is, and the stronger its effect becomes. In dense regions like galaxy clusters, the gravity of the matter present is strong enough to overcome dark energy's push, keeping those structures bound together. But in voids, where gravity is weak, dark energy's effect is more pronounced. This means that voids may be expanding faster than they would in a universe without dark energy. The Boötes Void, already vast, is growing larger over time as the space within it expands. The few galaxies in its interior are drifting farther apart, their isolation increasing. Billions of years from now, the void will be even emptier than it is today. Its galaxies separated by even greater gulfs of space. Some physicists have suggested that studying voids like Boötes could help us understand dark energy better. Because dark energy's effect is more pronounced in voids, careful measurements of how voids expand over time could reveal properties of dark energy that are harder to detect in denser regions. It's an elegant idea, using the universe's emptiest places to probe one of its deepest mysteries. There's also a relationship between void expansion and the cosmic microwave background that we touched on earlier. As photons from the cosmic microwave background pass through voids, they experience a slight change in energy due to the expansion of space within the void. This creates a subtle signal that can be detected and measured, providing another way to study both the void's properties and the nature of dark energy. The expansion of the Boötes Void is not something we can see happening in real time. The changes occur over millions of years, far too slowly for human eyes or even human civilizations to perceive directly. But through careful measurements repeated over years and decades, astronomers can detect these changes, seeing the void's evolution unfold like a flower blooming in extreme slow motion. And as we contemplate this expansion, this slow growth of emptiness, we're reminded that the universe is not static. Everything changes, even the voids, even the darkness between galaxies. The Boötes Void of today is not the same as the Boötes Void of 1 billion years ago, and it will be different still 1 billion years hence. We're observing not a fixed object, but a stage in an ongoing process, a chapter in a story that has no end. Gravity is usually thought of as an attractive force, pulling things together, creating structure where none existed before. But in the case of the Boötes Void, gravity's role is more subtle and more interesting. The void's gravitational influence, or rather the lack thereof, shapes the motion of galaxies around it and affects the flow of matter through the cosmic web. Imagine the void as a gravitational depression, a region where the pull of gravity is weaker than average because there's less mass present. Galaxies in the region surrounding the void feel this depression, tend to move along the void surface rather than across its volume. Astronomers can measure these peculiar velocities, the motions of galaxies that deviate from the uniform expansion of the universe. By mapping peculiar velocities around the Boötes Void, they can see how the void's presence affects the flow of matter on large scales. The pattern that emerges is consistent with what you'd expect from a large underdense region, galaxies moving away from the void's centre and toward its walls or toward other dense structures nearby. But the void's gravitational influence extends beyond its immediate surroundings. Create a pattern of mass distribution that generates gravitational fields spanning hundreds of millions of light years. These fields influence how galaxies move and how structure continues to evolve. There's also an effect called gravitational lensing, where the path of light is bent as it passes through a gravitational field. Massive objects like galaxy clusters can bend light dramatically, creating multiple images of distant galaxies or distorting them into arcs and rings. Voids, having less mass, bend light much more subtly, but they still have a measurable effect. When light from very distant galaxies passes through the Boötes Void, it's bent slightly less than it would be if it passed through an average density region of space. This creates a subtle signal in observations of distant sources, a kind of negative lensing that astronomers can detect with careful measurements. By studying this effect, they can map the distribution of matter within the void itself, including the dark matter that doesn't emit light. These gravitational lensing studies have revealed that while the Boötes Void is indeed very empty in terms of normal matter, it's not completely devoid of dark matter. There are faint traces of dark matter throughout the void's volume, forming a sparse web that connects the few galaxies present and links them to the structures outside the void. This dark matter is far less concentrated than in filaments, but it's there, a ghostly presence in the darkness. The void's gravitational field also affects the cosmic microwave background radiation in a way that's separate from the temperature effect we discussed earlier. As photons from the cosmic microwave background fall into and then climb out of gravitational wells, they gain and then lose energy. In a static universe, these effects would cancel out perfectly. But the universe is expanding, and structures are evolving, so there's a net effect called the integrated Sachs-Wolf effect. In the case of voids, which have negative gravitational potential, the integrated Sachs-Wolf effect creates cold spots in the cosmic microwave background. The Boötes Void contributes to such a cold spot, and by measuring this effect, astronomers can study the void's gravitational properties over cosmic time. It's yet another way the void makes itself known, another signal in the data that reveals its presence and properties. On a more philosophical level, the void's gravitational influence reminds us that absence can be as influential as presence. The Boötes Void shapes the universe around it not by what it contains, but by what it lacks. It's a negative space that defines the positive structure surrounding it, much like the space around a sculpture is as important to the artwork as the sculpture itself. As we move deeper into our journey through the void, past the halfway point of our time together, let this thought settle gently. The universe is shaped as much by its empty places as by its full ones. Structure exists in both presence and absence. In the bright filaments of galaxies and in the dark voids between them. Both are necessary, both are beautiful in their own way. And as we continue, we'll explore not just what the void is, but what it means, and what its existence tells us about our place in this vast, strange, wonderful cosmos. Behind every great scientific discovery are people, human beings with curiosity and patience, and the willingness to look carefully at data that might not seem particularly exciting at first glance. The discovery of the Boötes Void was no exception. It emerged from the work of a team of astronomers conducting what they thought would be a routine survey of galaxies, and it changed our understanding of cosmic structure. The team was led by Robert Kirshner, a young astronomer who would go on to make fundamental contributions to cosmology, including work on supernovae that would help reveal the accelerating expansion of the universe. In the late 1970s, he and his colleagues Augustus Oehmler, Paul Schechter and Stephen Schechtman were conducting a redshift survey of galaxies in the constellation Boötes. Their goal was straightforward: measure the distances to galaxies in this region of sky and create a three-dimensional map of their distribution. This required painstaking observational work. Each galaxy had to be observed spectroscopically, its light broken into a spectrum that would reveal how much its wavelengths had been shifted by the expansion of the universe. From that redshift they could calculate distance. The work was slow. Telescopes were less automated then, computers less powerful, detectors less sensitive. Each night of observing might yield redshifts for a few dozen galaxies at most. The team had to return to the telescope repeatedly over months and years to build up their sample. It was the kind of unglamorous patient labour that forms the foundation of astronomy, but rarely makes headlines. As the data accumulated, they began to plot the three-dimensional positions of the galaxies, and gradually a strange pattern emerged. In most regions of their survey, galaxies appeared at a range of distances, creating a distribution that looked more or less random with some clumping, what they expected. But in one area, there was a conspicuous gap. At certain distances, in a particular direction, they found almost no galaxies. At first, they suspected an error. Perhaps there was something wrong with their observing technique, or their telescope pointing, or their data reduction. They checked and rechecked their work. The gap remained. They expanded their survey, observing more galaxies in the surrounding region to confirm that the gap was real and not just a statistical fluke. The more they observed, the clearer it became. There was a vast region of space in front of them that contained far fewer galaxies than it should. The team published their findings in 1981, in a paper with the straightforward title, "A Million Cubic Megaparsec Void in Boötes." A megaparsec is about 3.3 million light-years, so they were announcing the discovery of a void roughly 100 million light-years across by their initial measurements, later refined to the 330 million light-years we know today. The response from the astronomical community was one of surprise and fascination. Large-scale structure surveys were still relatively new. The idea that the universe might have enormous voids was not widely anticipated. Kirshner's team had discovered something that challenged existing assumptions about how matter was distributed on the larger scales. In interviews later, Kirshner would describe the discovery as exciting, but also somewhat disconcerting. As astronomers, they were accustomed to finding things, new stars, new galaxies, new phenomena. Finding nothing, finding an absence so vast it defied easy explanation, was a different kind of discovery altogether. It was like being an explorer mapping a new continent and coming across a desert far larger than any previously known. The human side of this discovery is worth contemplating. These were people dedicating their careers to understanding the universe, spending long nights at telescopes, analysing data, writing papers, all driven by curiosity about what's out there. And what they found was a profound emptiness. A void so large it reshaped how we think about cosmic structure. Their willingness to trust their data, even when it showed something unexpected, led to a genuine expansion of human knowledge. The discovery of the Boötes Void in the late 1970s was made possible by technology that was, at the time, at the cutting edge of astronomy. Understanding that technology helps us appreciate both the achievement of the discovery and how far astronomical observations have come since then. The key tool was spectroscopy, the technique of breaking light into its component wavelengths. When you pass sunlight through a prism and create a rainbow, you're doing basic spectroscopy. When astronomers do spectroscopy on distant galaxies, they're looking for absorption and emission lines, specific wavelengths where light is absorbed or emitted by elements in the galaxy. These spectral lines act like fingerprints, telling us what elements are present in the galaxy and how fast the galaxy is moving. When a galaxy moves away from us due to the universe's expansion, all its spectral lines shift toward the red end of the spectrum. By measuring how much they've shifted, we can calculate the galaxy's velocity and, using Hubble's law, its distance. In the 1970s, spectroscopy was done using photographic plates or early electronic detectors attached to large telescopes. The process was time-intensive. You'd point the telescope at a galaxy, collect light through a spectrograph for perhaps an hour or more, then analyse the resulting spectrum to measure the redshift. In a good night, you might get data on a few dozen galaxies. The survey that discovered the Boötes Void used a 4-metre telescope, a substantial instrument but not the largest available. The team had to request time on this telescope, competing with other astronomers for access. when they were granted observing time. They had to use it efficiently, squeezing as much data as possible from each night despite weather, equipment issues, and the inevitable challenges of observational astronomy. The data reduction process, turning raw observations into usable measurements, was also more laborious then. Computers existed but were far less powerful than even a modern smartphone. Calculations that a laptop can do in seconds might have taken minutes or hours on the computers available in the late 70s. The team had to develop software to process their spectra, measure redshifts and plot galaxy positions in 3 dimensions. Today, spectroscopic surveys operate on a completely different scale. Modern instruments can measure spectra for thousands of galaxies simultaneously using multi-object spectrographs, with fibre optic cables or advanced detector arrays. Surveys like the Sloan Digital Sky Survey have measured distances to millions of galaxies, creating 3-dimensional maps of the universe far more detailed than anything Kirshner's team could have imagined. These modern surveys have found many more voids, cataloguing hundreds of them and studying their properties in detail. They've measured the void size distribution, discovering that while large voids like Boötes are rare, smaller voids are common. They've tracked how voids evolve over time by comparing nearby voids to distant ones, using the light travel time to look back into cosmic history. But technology has advanced beyond optical spectroscopy. Radio telescopes can map the distribution of hydrogen gas, including the sparse gas in voids. X-ray telescopes can detect hot gas and search for any unexpected sources of X-rays within voids. Gravitational wave detectors, while not directly observing voids, study phenomena that could be affected by the large-scale structure voids help create. We'll reveal the cosmic web in exquisite detail. These surveys will reveal the cosmic web in exquisite detail, showing not just the large voids like Boötes, but also smaller voids, the connections between voids, and the complex interplay of structure across billions of light years. The technology that revealed the Boötes Void to us continues to evolve, and each advancement brings new insights. But it all rests on the foundation laid by astronomers like Kirshner's team, who used the tools available to them with skill and persistence, and who trusted their observations even when those observations revealed something unexpected and strange. The Boötes Void is not alone. Once astronomers knew what to look for, once they had mapped enough of the universe in 3 dimensions, they discovered that voids are a common feature of cosmic structure. The universe is, in a sense, filled with emptiness, with vast regions where galaxies are rare and the darkness is profound. One of the better-known voids is the local void, which lies near our own Milky Way galaxy. It's smaller than Boötes, roughly 150 million light-years across, but it's nearby in cosmic terms, only about 45 million light-years from us at its closest point. The local void helps explain the peculiar motion of our local group of galaxies, which includes the Milky Way and Andromeda. We're being pushed away from the void and pulled toward the Virgo supercluster, a massive concentration of galaxies in the other direction. Then there's the Sculptor Void, located in the constellation Sculptor in the southern sky. It's comparable in size to Boötes and shares many of the same characteristics: a severe underdensity of galaxies, a roughly spherical shape, and walls of denser structure surrounding its volume. Studies of the Sculptor Void have revealed similar expansion patterns and temperature effects to those seen in Boötes, confirming that these voids operate by similar physical principles. The Giant Void, discovered in constellation Canes Venatici, is another impressive example. It stretches across roughly 300 million light-years and shows clear evidence of the void expansion effect we discussed earlier. Galaxies in its interior are moving apart from each other faster than you'd expect from the Hubble expansion alone, driven by the relative absence of gravitational attraction in the void's volume. Perhaps the most intriguing void discovery came more recently, with the identification of the CMB cold spot supervoid, also called the Eridanus supervoid. This is a collection of voids in the constellation Eridanus, that together create a particularly pronounced cold spot in the cosmic microwave background radiation. The supervoid is enormous, stretching across roughly 1 billion light-years, and its gravitational effect on the cosmic microwave background creates a detectable signal. There's an ongoing debate about whether the CMB cold spot can be entirely explained by this supervoid, or whether it might hint at something more exotic, perhaps a sign of structures beyond our observable universe, affecting the cosmic microwave background. Most cosmologists think the supervoid explanation is sufficient, but the question remains open. A reminder that even our most complete maps of cosmic structure still hold mysteries. Surveys have now catalogued hundreds of voids across the observable universe. They range in size from about 50 million light-years to several 100 million light-years in diameter. Statistical studies of these voids reveal patterns. Larger voids are rarer than smaller ones, following a distribution that matches predictions from cosmological simulations. The shapes of voids are generally ellipsoidal rather than perfectly spherical, reflecting the fact that structure formation doesn't proceed uniformly in all directions. These catalogues have allowed astronomers to study voids as a population rather than as isolated curiosities. They can ask questions like, how does void size relate to void emptiness? Do larger voids tend to be emptier, or is there no correlation? How do voids connect to each other and to the filaments surrounding them? How has the void population evolved over cosmic time? The answers to these questions help refine our understanding of cosmic structure formation. They test our cosmological models, confirming or challenging predictions about how gravity, dark matter and dark energy shape the universe on the larger scales. Each void is a natural laboratory where we can study these fundamental forces in action. Interestingly, while voids are common, truly large voids like Boötes remain rare. The universe can produce them, but they represent the tail end of the size distribution, the unlikely but not impossible outcomes of density fluctuations in the early universe. The Boötes Void stands out not because it's unique in kind, but because it's exceptional in magnitude, like a particularly massive star or an especially large galaxy cluster. And as we catalogue more voids and study their properties in greater detail, a picture emerges of a universe structured on multiple scales. There are small voids tens of millions of light-years across, medium voids around 100 million light-years, and rare large voids like Boötes pushing the upper limits of size. These voids, together with the filaments and clusters that surround them, form the cosmic web, the largest scale structure we know of in the universe. Voids are more than just empty spaces between galaxies. They're laboratories where cosmologists can test fundamental theories about the universe. Because voids are relatively simple structures, less complicated than galaxy clusters or filaments, they provide clean tests of cosmological models. What we learn from studying voids like Boötes helps us understand the universe as a whole. One of the key questions voids help answer is, how much dark energy is there, and how strong is its effect? Dark energy causes the universe's expansion to accelerate. But measuring this acceleration precisely is challenging. Voids, because they're expanding faster than average density regions, are sensitive to dark energy's influence. By measuring the expansion rate of voids and comparing it to predictions from different dark energy models, cosmologists can constrain the properties of dark energy. Voids also test our understanding of gravity on cosmic scales. General relativity, Einstein's theory of gravity, has been tested extensively in the solar system and around individual massive objects like black holes. But does it hold on scales of hundreds of millions of light-years? Voids help answer this question. The way matter moves around voids, the way light bends as it passes through them, all of this depends on whether gravity behaves according to general relativity or whether some modification is needed. So far, observations of voids are consistent with general relativity and with our standard model of cosmology, which includes dark matter and dark energy. This is reassuring, confirming that our understanding of the universe is on the right track. But scientists continue to look for any deviations, any hints that our theories might need adjustment. Voids, with their relative simplicity and large size, are ideal places to search for such hints. Another use of voids is as a probe of the initial conditions of the universe. The size distribution of voids depends on the spectrum of density fluctuations present in the early universe. By measuring how many voids of each size exist, cosmologists can test models of inflation, the brief period of rapid expansion that occurred moments after the Big Bang. Different inflation models predict slightly different fluctuation spectra, and voids provide one way to distinguish between these models. Voids also help us understand galaxy formation and evolution. By comparing galaxies in voids to galaxies in filaments or clusters, astronomers can isolate the effects of environment on galaxy properties. Why do some galaxies form stars rapidly while others are quiescent? How much does interaction with neighbouring galaxies matter? Void galaxies, isolated from neighbours, provide a control group that helps answer these questions. There's also interest in using voids to study the nature of dark matter. Different dark matter candidates predict slightly different structures on small scales. By examining the dark matter distribution within voids and around void galaxies, astronomers might be able to distinguish between different dark matter models. It's a challenging measurement, but future observations may make it possible. On a more speculative note, some physicists have proposed that voids might harbour undiscovered phenomena. Could there be exotic particles or fields that concentrate in voids rather than in dense regions? Could voids contain primordial black holes or other relics from the early universe? So far, there's no evidence for such things. But voids remain relatively unexplored compared to the bright filaments and clusters that have received more attention. What's clear is that voids are not just empty space to be ignored. They're an integral part of cosmic structure, and studying them provides insights that complement what we learn from studying galaxies and clusters. The universe is a tapestry woven from both light and darkness, from matter and void, and understanding either requires understanding both. As cosmological surveys continue to improve, as we map larger volumes of space in greater detail, voids will play an increasingly important role in cosmology. They're no longer just curiosities, but essential probes of the universe's fundamental properties. The Boötes Void, that vast darkness discovered in the late 1970s, has become a window into the deepest questions we can ask about reality itself. One of the most powerful tools modern cosmologists have is the ability to simulate the universe on a computer. These simulations start with the conditions present in the early universe, tiny fluctuations in density scattered across space, and evolve them forward according to the laws of physics. The result is a virtual universe that can be compared to observations of the real universe. Creating these simulations is a monumental computational challenge. A typical cosmological simulation might track billions of particles representing dark matter, each one interacting gravitationally with every other particle. The calculations required are staggering, demanding some of the world's most powerful supercomputers running for weeks or months to simulate a single volume of space evolving over cosmic time. But the results are worth the effort. When astronomers run these simulations and examine the structures that form, they see the cosmic web emerge naturally. Filaments of galaxies connected by thin threads of matter. Nodes where filaments intersect, creating massive clusters, and voids. Vast regions where galaxies are rare. The simulations reproduce the observed structure of the real universe with remarkable fidelity. Within these simulated universes, voids form through the same process we described earlier. Regions that start slightly underdense remain underdense as matter flows out of them toward denser regions. Over billions of simulated years, these underdense patches grow into voids with properties very similar to observed voids like Boötes. Astronomers can examine these simulated voids in ways impossible with real observations. They can track individual particles as they move out of the void region. They can see exactly how dark matter distributes itself within the void. They can measure the void's expansion rate at different times in its history. They can even run multiple simulations with slightly different initial conditions or different physical parameters to see how voids change. These simulations have confirmed that voids like the Boötes Void are expected consequences of structure formation in our universe. They're not anomalies requiring special explanations, but natural outcomes of gravitational instability operating on primordial density fluctuations. The fact that simulations produce voids with similar sizes, shapes, and properties to observed voids is strong evidence that our understanding of cosmic structure formation is correct. But simulations also make predictions that can be tested against future observations. For example, simulations predict that the dark matter distribution within voids should follow certain patterns, with thin filaments of dark matter connecting the few galaxies present and forming a sparse web within the void's volume. As observational techniques improve, astronomers may be able to detect this dark matter structure through gravitational lensing, confirming or challenging the simulation predictions. Simulations also allow astronomers to study void evolution over time. By comparing voids at different stages in a simulation's history, they can see how voids grow, how their shapes change, how the matter distribution within them evolves. This provides a dynamical picture of voids that complements the static snapshots we get from observations. One fascinating prediction from simulations is that voids should merge, just as galaxies merge. When two voids expand and their boundaries meet, they can combine into a single larger void. This process happens slowly, over billions of years, but simulations show it occurring regularly. Whether we can observe void mergers in the real universe is an open question, one that future surveys may help answer. Simulations have also been used to study how voids affect other cosmic phenomena. For instance, how do voids influence the propagation of cosmic rays? High-energy particles that travel through space, how do they affect the formation of the first stars and galaxies in the early universe? How do they channel the flow of matter along the cosmic web? Simulations can explore these questions, generating predictions that observational astronomers can then test. There's a beautiful interplay here between observation and theory. Observations discover phenomena like the Boötes Void. Simulations help explain those phenomena and make predictions about details we can't yet observe. Those predictions guide future observations, which either confirm the simulations or reveal surprises that require new physics to explain. It's an iterative process, a dialogue between what we observe and what we calculate, and it drives our understanding forward. The simulations aren't perfect, of course. They make simplifying assumptions, they have limited resolution, and they can't include every physical process that might be important. But they're remarkably good at reproducing the large-scale structure of the universe, and they give us confidence that we understand the basic mechanisms by which voids form and evolve. As computers become more powerful and simulation techniques more sophisticated, the virtual universes cosmologists create become more detailed and realistic. Future simulations may include not just dark matter, but also gas dynamics, star formation, black hole growth, and the complex feedback processes that affect galaxy evolution. These simulations will provide even richer insights into how voids fit into the cosmic web and what their existence tells us about the universe. And as you drift deeper into rest, consider this. Somewhere in a vast computer simulation, a virtual void much like the Boötes Void is expanding. Its simulated galaxies drifting apart according to mathematical laws that mirror the real laws governing our universe. The fact that we can create such simulations, that we can use mathematics and computation to mirror reality, is itself a profound achievement, a testament to human curiosity and our capacity to understand the cosmos we inhabit. There's a quality to the Boötes Void that's difficult to capture in scientific language, a quality that has more to do with feeling than with fact. Imagine, if you can, being somehow positioned at the centre of this vast emptiness. The nearest galaxies would be tens of millions of light years away in every direction. faint smudges of light on the edge of what even a powerful telescope could detect. In such a place, the sky would be profoundly dark. On Earth, when we look up at night, we see thousands of stars from our own Milky Way galaxy. A river of light arcing across the sky, but from the centre of the Boötes Void, there would be no Milky Way overhead, no nearby stars at all. The sky would be dominated by the cosmic microwave background radiation, that faint afterglow of the Big Bang, too faint and too red-shifted for human eyes to see. Any hypothetical observer in such a place would experience a darkness unlike anything we can imagine from our position within a galaxy. There would be no constellations, no planets, no bright stars to serve as navigation markers, just an almost uniform darkness punctuated by a few incredibly distant, incredibly faint smudges that careful observation would reveal as galaxies on the void's edge. This isolation might seem lonely, even frightening, but there's another way to think about it. In the void, free from the gravitational pull of nearby masses, free from the light pollution of countless stars, one would have an unobstructed view of the universe at large. The most distant galaxies would be visible without nearby bright objects overwhelming them. The cosmic microwave background could be studied without contamination from local sources. From a scientific perspective, fills our solar system. The centre of the fills our solar system. The centre of the Boötes Void would be the ultimate version of such a location, a place where the local environment is as close to a perfect vacuum as the universe offers. But there's also a philosophical dimension to this thought experiment. The void reminds us that emptiness is a fundamental part of the universe, as much a part of reality as matter and energy. We tend to focus on the bright things, the stars and galaxies, the planets and nebulae, but the darkness between them is not merely absence, it's space itself, the arena in which all events occur, and it has properties and structure just as matter does. In many spiritual traditions, emptiness is not seen as negative but as potential, as the space from which things can emerge. The Buddhist concept of shunyata, often translated as emptiness, refers not to nihilistic nothingness, but to the absence of inherent independent existence. Things arise in dependence on conditions, and emptiness is the recognition of this interdependence. The Boötes Void, from this perspective, is not mere absence, but a different kind of presence. It's structured emptiness shaped by the same forces that shape the bright filaments of galaxies. It has temperature, expansion rate, gravitational potential. It affects the cosmic microwave background, bends light passing through it, and influences the motion of galaxies around it. It is, in every sense, real. This reality of emptiness challenges us to expand our conception of what matters, quite literally. We evolved to pay attention to things, to objects we can see and touch. Empty space doesn't register as important to our ancestral survival instincts. But in the cosmos, empty space is where most of the universe exists. By volume, the universe is overwhelmingly void. The bright galaxies and stars that capture our attention occupy only a tiny fraction of cosmic volume. If we could somehow travel to the Boötes Void, if we could experience that profound darkness firsthand, perhaps we would return with a different perspective on our own existence. We live in a galaxy filled with hundreds of billions of stars in a cosmic neighbourhood teeming with other galaxies. We're in one of the bright places, one of the nodes in the cosmic web where matter is accumulated. Our experience of the universe is, in that sense, unusual, privileged perhaps, but certainly not representative of cosmic space as a whole. And yet, even in that acknowledgement, there's a kind of comfort. The void and the filaments are part of the same structure. The darkness and the light define each other. We couldn't have galaxies without voids, couldn't have concentrations of matter without regions where matter is scarce. The universe needs both, and both are beautiful in their way. Time behaves strangely on cosmic scales, and nowhere is this more apparent than when we consider the void's existence through time. The Boötes Void we observe today is a snapshot of how it appeared hundreds of millions of years ago, when the light we detect began its journey toward us. But the void has a history that stretches back billions of years, and a future that will extend billions more. In the very early universe, before the void existed, the region that would become Boötes was part of the nearly uniform soup of matter and radiation that filled all of space. It was perhaps slightly less dense than average, but the difference was minuscule, detectable only as a tiny temperature fluctuation in the cosmic microwave background radiation. As the universe expanded and cooled, and as the first structures began to form under gravity's influence, this region's slight underdensity meant that matter flowed out of it rather than into it. This process unfolded over hundreds of millions of years, a timescale so vast that it's hard to comprehend. For context, the entire span of human existence, from our earliest ancestors to the present day, is only a few million years, a tiny fraction of the time it took for the void to form. By the time the universe was perhaps 2 or 3 billion years old, the Boötes region had developed into a recognizable void, a volume of space significantly emptier than its surroundings. The few galaxies that formed within it did so early, during the period when there was still enough local matter to fuel their initial growth. As the universe continued to age, these void galaxies evolved slowly, their star formation rates declining as their gas supplies were consumed and not replenished. Today, about 14 billion years after the Big Bang, we observe the Boötes Void in what might be considered its mature state. It's a well-defined structure, clearly distinct from the surrounding filaments and clusters. Its expansion continues, driven by the overall expansion of the universe and by dark energy's influence. The void is growing larger, its interior becoming emptier still, as the galaxies within it drift farther apart. But what of the void's future? If we could fast forward billions of years and observe the Boötes Void as it will be rather than as it was, what would we see? The answer depends on the ultimate fate of the universe itself, which depends on dark energy's properties. If dark energy remains constant in strength, what cosmologists call the cosmological constant scenario, then the universe will continue expanding forever, and that expansion will continue accelerating. The Boötes Void will grow larger and emptier. The few galaxies within it will drift farther apart, becoming increasingly isolated. Eventually they'll be so far apart that light from one will no longer be able to reach the others, each galaxy becoming a lonely island in an expanding darkness. In this scenario, the void will eventually dominate the universe. As expansion continues and galaxies drift apart, more and more of space will become void-like, empty volumes where galaxies are rare or absent. Billions of years in the future, a hypothetical observer anywhere in the universe might find themselves in a situation similar to being in the centre of the Boötes Void today, surrounded by vast darkness, with only a few faint distant galaxies visible. Some cosmologists call this the, quote, one of the universe, a state of maximum entropy where everything is spread out so diffusely that no significant events can occur. Stars will have burned out, black holes will have evaporated through Hawking radiation, and what remains will be a cold, dark and incredibly dilute soup of particles drifting through ever-expanding space. But there are other possibilities. If dark energy's strength changes over time, the future could be different. Some models suggest dark energy might weaken, allowing gravity to eventually halt the expansion and reverse it, leading to a big crunch where the universe collapses back on itself. In such a scenario, voids would shrink, matter would flow back into them, and the cosmic web would contract. Other models suggest dark energy might strengthen, leading to a big rip where the acceleration becomes so strong that it eventually tears apart galaxies, solar systems, planets, and even atoms. In this scenario, the Boötes Void would experience even more rapid expansion, until the fabric of space-time itself becomes unstable. We don't yet know which scenario is correct. Current observation suggests the cosmological constant model is most likely, but uncertainties remain. The void's future, like the universe's future, is still partially unknown, a reminder that even with all our scientific progress, fundamental questions remain unanswered. But perhaps there's something appropriate about that uncertainty. The void began as a quantum fluctuation in the earliest moments of the universe, a random variation in density that happened to occur in the region we call Boötes. From that tiny seed, shaped by physical laws operating over billions of years, grew this vast structure we now observe. And that structure will continue to evolve, shaped by those same laws, into a future we can only partially predict. Time in the void is patient. Changes unfold over millions and billions of years, timescales that make human history seem like a fleeting instant. And yet, we can observe these changes, can measure the void's expansion, can predict its future evolution. We've become, in a sense, witnesses to cosmic time, able to perceive processes that dwarf us in scale, but not in significance. Behind the Boötes Void's vast darkness lies mathematics, elegant equations that describe how structure forms, how gravity works, how space expands. Understanding the void fully requires engaging with this mathematics, even if only conceptually, because the math reveals patterns and relationships that words alone cannot capture. The fundamental equation governing the void's formation is the Friedmann equation, derived from Einstein's general relativity. This equation relates the universe's expansion rate to its energy content, including matter, radiation, and dark energy. It tells us how the universe expands over time and how that expansion is affected by what the universe contains. When cosmologists study structure formation, they add perturbations to the Friedmann equation, small variations in density that represent the primordial fluctuations we've discussed. These perturbations evolve according to additional equations that describe how gravity amplifies density differences and how expansion works to smooth them out. The interplay between these two effects, gravitational clumping and cosmic expansion, determines whether a region becomes a filament or a void. In the case of the Boötes Void, the mathematics shows that the initial underdensity was just right to grow into a void, rather than being smoothed out by expansion, or turned into a filament by gravitational collapse. The region was underdense enough that matter flowed out of it, but not so underdense that it violated the observed smoothness of the cosmic microwave background. The math also describes how voids expand. The expansion rate within a void depends on the void's density, the surrounding matter distribution, and dark energy's influence. Cosmologists can write down equations that predict how fast the Boötes Void should be expanding, and these predictions can be tested against observations. So far, observations match predictions remarkably well, confirming our mathematical understanding of void physics. Gravitational lensing, which we touched on earlier, is also described by mathematics. Einstein's equations tell us how mass curves space-time, and that curvature determines how light paths bend. The Boötes Void, with its low mass, creates a negative curvature compared to average space, causing light to bend slightly outward rather than inward as it passes through. The magnitude of this effect can be calculated precisely, and those calculations guide observational searches for lensing signals. There's also a mathematical description of how the void's temperature relates to its density. The equations of thermodynamics and cosmology combine to predict the temperature of gas in voids, and those predictions can be tested against observations of the cosmic microwave background. Again, the match between prediction and observation is good, giving us confidence in the mathematics. Perhaps what's most beautiful about the mathematical description of the void is its universality. The same equations that describe the Boötes Void also describe every other void in the universe. The same principles that govern structure formation here govern it everywhere. As far as we can tell, the mathematics is not specific to one location or one time, but appears to be a fundamental description of how the universe works. This universality is what allows us to use voids as probes of fundamental physics. If the math describing voids were different in different places or at different times, we couldn't use them to test cosmological models. But because the math is universal, deviations from predictions would indicate new physics, something beyond our current understanding. There's also a philosophical dimension to this mathematical description. The fact that the universe can be described by mathematics, that its behaviour follows equations we can write down and solve, is itself remarkable. Why should the universe be mathematical? Why should abstract concepts like numbers and equations correspond to physical reality? These are questions that have occupied philosophers and scientists for centuries. Some argue that mathematics is discovered, that it exists independently of human minds, and we simply uncover its truths. Others argue that mathematics is invented, a human creation that happens to be useful for describing nature. Regardless of which view is correct, the effectiveness of mathematics in describing phenomena like the Boötes Void is undeniable. The void doesn't know it's obeying mathematical laws. It simply exists, evolving according to the fundamental forces and properties of the universe, but we can observe it, measure it, and describe it using 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Measure it and describe it using equations. We can predict how it will behave in situations we haven't yet observed. We can connect its properties to fundamental constants like the gravitational constant, the speed of light, and the Hubble parameter. In this way, mathematics becomes a bridge between the human mind and cosmic reality. We sit here on Earth, a tiny planet in a galaxy far from the Boötes Void, and yet through mathematics we can understand that void's properties, its history, and its future. We can place it in a broader context, seeing it not as an isolated phenomenon, but as one instance of a general process that occurs throughout the universe. And as complex as the mathematics can become, as filled with Greek letters and integral signs and tensor notation, at its heart it expresses something simple. The universe follows rules, and those rules can be understood. The Boötes Void is not arbitrary or chaotic. It's a structured emptiness, shaped by laws we can comprehend, and that comprehension is one of humanity's greatest achievements. For all our observations and measurements, for all the data we've collected and the simulations we've run, there's much about the Boötes Void we still cannot see and may never fully know. The void holds mysteries that current technology cannot resolve, and questions that may require entirely new physics to answer. One such mystery is the precise distribution of dark matter within the void. We know dark matter is there, inferred from gravitational effects and simulations, but we cannot observe it directly. We can map its large-scale distribution through gravitational lensing, and through its effect on the motion of the few galaxies present, but the fine details remain hidden. Does dark matter form small clumps within the void, mini halos too small and diffuse to have captured enough normal matter to form visible galaxies? Or is it spread uniformly, a smooth background density lower than in filaments but still present? Different dark matter models make different predictions, but distinguishing between them requires observations we cannot yet make. There's also the question of what exactly fills the space within the void. We call it a vacuum, but even the vacuum isn't truly empty. Quantum field theory tells us that empty space is filled with virtual particles, quantum fluctuations that constantly appear and disappear. These fluctuations may contribute to dark energy, the mysterious force driving the universe's accelerated expansion. In the void, where normal matter is scarce and dark matter is diffuse, these quantum effects might be more apparent than in denser regions, but detecting them is extraordinarily difficult. The energies involved are tiny, and distinguishing quantum vacuum effects from other phenomena requires precision we don't yet have. Another unseen aspect of the void is its evolution on short timescales. We can measure how the void has changed over cosmic history by comparing it to voids at different distances, using light travel time to look into the past, but we cannot watch a single void evolve over human timescales. The changes are too slow, unfolding over millions of years. This means there might be dynamic processes occurring in the void that we're simply not fast enough to observe. Perhaps gas flows into and out of the void in currents we cannot detect. Perhaps the few galaxies present occasionally interact in subtle ways that would only be visible if we could watch for millennia. There's also the possibility of completely unexpected phenomena in voids. Physics at extreme scales, whether extremely large or extremely small, sometimes reveals surprises. Could there be particles or fields that concentrate in voids rather than in dense regions? Things we've never detected because we've focused our observations on galaxies and clusters. Some theoretical physicists have speculated about such possibilities. Perhaps certain types of dark matter or dark energy cluster in voids. Perhaps there are topological defects from the early universe, cosmic strings or domain walls that preferentially exist in underdense regions. Perhaps the vacuum itself has different properties in voids than in normal space. So far, there's no evidence for any of these exotic possibilities, but the absence of evidence is not evidence of absence, especially when our observational capabilities are limited. The Boötes Void is simply too far away and too faint to study with the detail we can bring to nearby objects. Future technologies may change this. Next-generation telescopes, both on the ground and in space, will be more sensitive and will observe across a wider range of wavelengths. They may detect subtle signals from the void that current instruments miss. They may reveal structures or phenomena that will surprise us, just as the void's initial discovery surprised astronomers in the late 1970s. Billions of years ago is just reaching us. Billions of years ago is just reaching us now, and light from the void's current state won't reach us for billions more years. We're always observing the past, and the present state of the void is, in a strict sense, unknowable. This limitation applies to all of astronomy, of course, not just to void studies. But it's particularly poignant when considering something as vast and distant as Boötes. The void we study existed in that form hundreds of millions of years ago. What it looks like now, we can only infer from our understanding of how voids evolve. Perhaps most profoundly, we cannot fully know what it would be like to experience the void firsthand. We can calculate numbers, plot graphs, create simulations, and write equations. But the actual experience of being in such a place, surrounded by that vast darkness, is beyond our reach. We're storytellers trying to describe a place we can never visit, using instruments and mathematics to build a picture of something fundamentally alien to our everyday experience. And yet, for all these limitations, we've learned an extraordinary amount. We've mapped the void's extent, measured its properties, placed it in cosmological context, and understood its formation and evolution. We've turned an absence into a presence, made the invisible visible through careful observation and reasoning. What we cannot see may be vast, but what we can see is already remarkable. The Boötes Void invites us to contemplate loneliness on a cosmic scale, but also to recognize the connections that bind even the most isolated parts of the universe together. The galaxies within the void, separated by tens of millions of light years from their nearest neighbours, might seem unimaginably lonely. And yet, they're part of the same cosmic web as everything else, connected by gravity, by history, and by the underlying structure of space-time itself. Consider a galaxy near the void's centre. Its night sky would be almost empty, no nearby galaxies visible without powerful telescopes. If intelligent life arose in such a galaxy, their understanding of the universe would be fundamentally different from ours. They would not see the Milky Way's neighbouring galaxies, would not observe the rich structure of galaxy clusters nearby. Their cosmology would develop differently, perhaps more slowly, with fewer nearby examples to study. this hypothetical civilization would still see the cosmic microwave background, still observe distant galaxies on the void's edge, still detect the expansion of the universe. They would eventually arrive at similar conclusions about cosmology as we have. But the path would be different, the evidence less immediately apparent, the isolation more profound, and yet that very isolation might confer advantages. Void galaxies experience fewer mergers and interactions, allowing them to maintain their structure over cosmic time. The gas within them is less likely to be stripped away by ram pressure or tidal forces. They're laboratories of gentle evolution, places where galaxies can age slowly and peacefully. From our perspective, embedded in a relatively dense part of the cosmic web, void galaxies might seem deprived. But perhaps from their perspective, if perspective can be attributed to galaxies, our environment would seem chaotic and violent. Constant interactions, mergers, disruptions. A sky crowded with neighbours. Gravitational fields overlapping and interfering. Perhaps the void galaxies have achieved a kind of cosmic solitude that's valuable in its own right. This raises interesting philosophical questions about isolation and community. Is connection always better than solitude? Do structures need neighbours to be complete, or can they exist meaningfully in isolation? These questions apply to galaxies and to human communities alike. In human terms, we value both connection and solitude. We need community, interaction and relationship with others, but we also need quiet, reflection and time apart. The richest human experience balances both, neither being entirely isolated nor constantly immersed in social connection. Perhaps the universe itself reflects this balance. The cosmic web includes both the dense clusters where galaxies crowd together and the empty voids where galaxies are rare. Both are necessary to the overall structure. Neither is better or worse, just different expressions of how matter organises itself under gravity's influence. The void galaxies are lonely, but not alone. They're part of the same universe as everything else, formed by the same processes, following the same laws. The light from quasars billions of light years away passes through the void just as it passes through filaments. Cosmic rays from distant supernovae traverse the void's volume. The neutrinos streaming out from nuclear reactions in stars throughout the universe pass through the void without pause. In this sense, the void is not separate from the rest of the universe, but fully integrated into it. It's a region where matter is scarce, yes, but it's not disconnected or cut off. Information flows through it, in the form of light and particles and gravitational waves. The void is permeable, transparent. Part of the cosmic conversation, even if it has little to say itself. This connects to a deeper truth about the universe. Everything is related to everything else, not just locally, but cosmically. The matter in your body was forged in stars that exploded billions of years ago, possibly in galaxies on the other side of the observable universe. The photons entering your eyes right now have travelled through countless regions of space, perhaps even through voids like Boötes. The universe is a unity, a single interconnected system. Voids and filaments, galaxies and empty space, dark matter and baryonic matter, all of it fits together into a coherent whole. We divide it up for study, naming parts and measuring them separately, but those divisions are human constructs. The universe doesn't recognize boundaries between voids and filaments. It's all one continuous structure. From this perspective, the Boötes Void is not an absence but a presence, not nothing but a particular configuration of something, a region where the cosmic web takes a specific form. It's as essential to the universe as any galaxy cluster, as meaningful as any supernova, as worthy of study as any distant quasar. And perhaps this is the deepest lesson the void has to teach us, that emptiness can be meaningful, that absence can have structure, that the spaces between things are as important as the things themselves. In music, the rests between notes give the melody its shape. In art, negative space defines the positive forms. In life, the The quiet moments of solitude balance the active moments of engagement. The Boötes Void is the universe's moment of silence, a cosmic rest in the symphony of structure formation. And in that silence, if we listen carefully, we can hear echoes of the deepest truths about existence, about how something emerges from nothing, how structure arises from uniformity, how the universe creates beauty from the simplest initial conditions and the most fundamental physical laws. As we prepare to drift deeper into the final act of our journey together, let this thought rest in your mind. You are connected to the Boötes Void as you are connected to everything in the universe. The atoms in your body have travelled through cosmic voids, have been part of stars and nebulae, have participated in the great cosmic dance of matter through space and time. The void is not separate from you, but part of the same grand structure that includes you, that includes all of us, all of matter, all of existence. And in recognizing that connection, perhaps we find a deeper peace with the vast, strange, beautiful universe we call home. In contemplating the Boötes Void, we've travelled across hundreds of millions of light years and billions of years of time. We've explored emptiness on a scale that defies easy comprehension, considered physics at the universe's larger scales, and examined how structure emerges from the simplest beginnings. And in doing all this, something shifts in how we see ourselves and our place in the cosmos. The void gives us perspective, not just intellectually, but emotionally and spiritually. When we grasp, even partially, the scale of something like the Boötes Void, our everyday concerns seem to shrink correspondingly. The worries that felt so large this morning, the anxieties about tomorrow, the regrets about yesterday, they don't disappear, but they take on a different quality when set against the backdrop of cosmic immensity. This can be comforting or unsettling, depending on how we approach it. Some find the universe's vastness isolating, a reminder of how small and insignificant we are in the grand scheme of things. But there's another way to think about it, a way that finds meaning rather than meaninglessness in cosmic scale. Yes, we're small. A human being is perhaps 2 meters tall. Earth is less than 13,000 kilometers in diameter. Our solar system is a few light hours across. Even our entire galaxy is just 100,000 light years wide. Compared to the Boötes Void's 330 million light years, we're infinitesimally tiny, less than a grain of sand compared to an ocean. But we're also the part of the universe that's capable of understanding the rest of it. We're made of atoms that were forged in stars, arranged by evolution into patterns capable of thought, curiosity, and comprehension. We can look at the Boötes Void, measure it, study it, and grasp what it means. We're the universe's way of knowing itself. This perspective doesn't make us more important in any objective sense. The void doesn't care that we exist, doesn't know we're observing it, doesn't benefit or suffer from our attention. But our capacity to observe and understand is itself remarkable, an outcome of billions of years of cosmic evolution that's no less significant than the formation of galaxies or voids. The void reminds us that we're part of something much larger than ourselves, connected to a cosmos that extends far beyond what we can directly perceive. Every atom in our bodies has a history that stretches back to the Big Bang, that includes time spent in primordial clouds, in the cores of stars, in the debris of supernovae, in the molecular clouds where new stars form. Some of the atoms in your body may have once been part of gas that flowed through the Boötes Void, participating in that early exodus of matter from under dense regions toward filaments and clusters. They travelled billions of light years, were incorporated into stars that lived and died, were scattered into space again, eventually found their way to the molecular cloud that formed our sun and solar system, became part of Earth, and now constitute you. This is literally true. The atoms in your body are ancient and well-travelled. Has seen the universe from perspectives you can only imagine. Recognizing this connection doesn't solve life's problems or answer its difficult questions. You'll still have challenges tomorrow, still face uncertainties and difficulties. But perhaps holding this cosmic perspective even lightly can provide a kind of ground beneath those challenges, a reminder that you're part of something vast and ancient and ongoing. The Boötes Void has existed for billions of years and will exist for billions more. Human civilizations rise and fall in what amounts to an instant on cosmic timescales. Individual human lives are briefer still, and yet our lives matter to us. And that mattering is itself significant. We're the part of the universe that assigns meaning, that values beauty, that pursues understanding. The void doesn't need us to study it. It would exist exactly as it does whether we ever discovered it or not. But we're enriched by studying it, by expanding our knowledge of the cosmos, by satisfying our curiosity about what's out there, and in some small way, through our observations and theories and conversations, we change the universe too. We become part of its story, contributors to its ongoing evolution, not just passive observers, but active participants. This perspective, this sense of being simultaneously insignificant and deeply meaningful, of being tiny specks in a vast cosmos, but also the cosmos's eyes and ears and mind, is perhaps the greatest gift the void can give us. It's a perspective that can help us hold our local concerns lightly while still taking them seriously, that can provide comfort in difficult times without dismissing difficulty, that can inspire wonder without demanding worship. As you rest here, in this quiet moment between waking and sleep, you carry within you atoms that have journeyed through voids, through stars, through billions of years of cosmic history. You are the universe contemplating itself. A temporary arrangement of ancient matter capable of thought and feeling and understanding, and that is enough. That is in fact extraordinary. Throughout our journey through the Boötes Void, we've encountered many things we cannot fully know. The precise distribution of dark matter within the void, the current state of galaxies we observe only as they were hundreds of millions of years ago, the ultimate fate of the void billions of years in the future, the nature of the dark energy causing the universe's expansion to accelerate. Science often focuses on what we know, presenting discoveries and conclusions with confidence. But equally important, perhaps more important, is recognizing what we don't know. Good science acknowledges uncertainty, embraces the provisional nature of knowledge, and maintains humility in the face of cosmic mystery. The Boötes Void, like much of the universe, exists at the edge of our understanding. We can measure its extent and density, can place it in cosmological context, can simulate its formation and evolution. But large uncertainties remain. The void might be slightly larger or smaller than our best estimates. Its interior might contain structures we haven't detected. Its formation might have involved processes we don't yet understand. This uncertainty isn't a failure of science, but an honest acknowledgement of science's limitations. We're building models of the universe using incomplete data, trying to understand phenomena that occur on scales vastly larger than anything in our everyday experience. That we can understand as much as we do is remarkable. That questions remain is natural. There's a temptation, in both science and in life more generally, to pretend we know more than we do, to project confidence even when uncertainty is warranted. But there's also wisdom in acknowledging uncertainty, in saying quote 4 or quote 5 when those are the honest answers. In the case of the Boötes Void, we don't know exactly why it's so large. We can explain it in general terms, as a rare fluctuation in the early universe's density field that happened to occur in this region. But why this particular region? Why this particular size? These questions have no answers beyond chance or random variation, which might feel unsatisfying but is nonetheless truthful. We don't know if there are processes occurring in the void that we haven't detected or imagined. We're reasonably confident we understand the basic physics, But quote 8 quote is not quote 9 quote. History is full of examples where scientists were confident about something that later proved wrong or incomplete. We don't know the ultimate fate of the void because we don't fully understand dark energy. Will the void expand forever, its galaxies drifting apart into increasing isolation? Will expansion eventually reverse? We don't know if there's anything fundamentally special about the Boötes Void beyond its size. Is it just an unremarkable large void, or does it hold secrets about cosmic structure formation that we haven't yet uncovered? Are there subtle differences between it and other voids that might reveal new physics? We can't rule out such possibilities, even as we also can't confirm them. This uncertainty extends beyond the void to cosmology generally and to much of science. We don't know what dark matter is despite decades of searching. We don't know what dark energy is despite measuring its effects. We don't know if the universe is infinite or finite, if there are other universes beyond our observable horizon, if the laws of physics are the same everywhere and every when. But here's what's interesting. We've learned to be comfortable with uncertainty in science, to work productively despite not having all the answers. We build models that are useful even when they're not complete. We make predictions that are testable even when they're not certain. We continue exploring, observing, theorizing, knowing that every answer leads to new questions. This scientific humility, this willingness to say we don't know without giving up the search for knowledge, is applicable to life beyond science. We don't know what the future holds, don't know with certainty what the right choice is in difficult situations, don't know how our stories will end. We live with uncertainty whether we acknowledge it or not. Perhaps the void can teach us something about this. It exists in its vast emptiness, indifferent to our understanding or lack thereof. It doesn't need us to fully comprehend it. It simply is. And we can study it, can build partial understanding, can acknowledge what we don't know, and can find peace with that mixture of knowledge and ignorance. The alternative, pretending we know everything, or refusing to explore because we can't know everything, seems much worse. Better to embrace uncertainty as an inherent part of existence, to find comfort in partial knowledge, to recognize that the journey of understanding is valuable even when we can't reach a final destination. The Boötes Void, in its mysterious vastness, invites us to be comfortable with not knowing, to accept that some questions may never be fully answered, and to find beauty in the mystery itself. The darkness between the galaxies holds secrets. And perhaps some of those secrets are meant to remain secret, at least for now, at least for us, finite beings trying to comprehend the infinite. After all our exploration of emptiness, of voids and darkness and absence, it's worth stepping back to appreciate the larger pattern the Boötes Void helps create. Because the void isn't isolated. It's part of the cosmic web, that magnificent large-scale structure that emerges when matter organizes itself under gravity's influence over billions of years. If you could see the cosmic web in its entirety, if you could somehow perceive all the galaxies in the observable universe simultaneously in 3 dimensions, you would see a pattern of breathtaking beauty. Filaments of galaxies stretching across hundreds of millions of light years, interconnecting at massive clusters, sheets and walls of galaxies forming surfaces that bound the voids, and the voids themselves, vast bubbles of darkness giving shape to the bright structures around them. This pattern wasn't designed. No intelligence directed its formation. It emerged naturally from simple initial conditions, tiny variations in density in the early universe, and simple physical laws, primarily gravity and the expansion of space. The same equations that govern how an apple falls from a tree also govern how galaxies cluster across cosmic distances. The simplicity of the laws contrasts beautifully with the complexity of the structure they create. The cosmic web is an example of what scientists call an emergent pattern, something that arises from simple rules applied over and over at different scales. Snowflakes show emergent patterns. Each one is unique, yet all follow similar structural principles that emerge from how water molecules bond when freezing. Coastlines show fractal patterns, similar in structure whether you look at kilometres or metres. The cosmic web shows patterns too, self-similar across scales. Within this web, voids like Boötes play an essential role. They're not defects or failures of structure formation, but integral parts of the pattern. Just as a painting needs both dark and light areas to create contrast and depth, the cosmic web needs both dense regions and empty ones to create its structure. The filaments wouldn't have the shape they do without the voids pushing back against them, creating boundaries and defining edges. The voids wouldn't exist without the filaments drawing matter away from under dense regions. The two are co-created, arising together from the same process, neither able to exist without the other. There's an aesthetic quality to this that transcends scientific description. The cosmic web is objectively beautiful, in the same way a great piece of music or a stunning landscape is beautiful. It has balance, proportion, pattern and variation. It shows both order and chaos, regularity and randomness, simplicity and complexity. Artists have tried to capture this beauty, creating visualizations of the cosmic web using data from galaxy surveys. These visualizations show the filaments as glowing threads, the clusters as bright nodes, and the voids as dark spaces between. Some are coloured according to galaxy density or type, creating rainbows of cosmic structure. Others are rendered simply in black and white, showing only the distribution of matter across space. Mathematicians and physicists find beauty in the equations describing cosmic structure, in the way solutions to the Friedmann equation predict exactly the kind of web structure we observe. There's an elegance to how gravity and expansion balance, how initial conditions evolve into final structures, how the mathematics mirrors reality. But you don't need to be a scientist or artist to appreciate the cosmic web's beauty. Simply knowing it exists, knowing that the universe has organised itself into this magnificent pattern, can be awe-inspiring. We're part of this pattern, embedded in it, made from matter that has participated in the cosmic dance of structure formation. The Boötes Void, seen in this context, is a masterpiece of cosmic architecture. Its vast emptiness is as carefully sculpted as Michelangelo's David, though sculpted by gravity rather than by chisel. Its boundaries are as precisely defined as any geometric construction, though defined by the flow of matter rather than by compass and straightedge. Its interior space is as meaningful as the interior of a cathedral, though filled with darkness rather than light. When we study the void, we're not just doing science. We're also appreciating art, encountering beauty, experiencing wonder. These responses are human, subjective, not part of the objective scientific description, but they're no less real for being subjective, no less valuable for being human. The universe doesn't need us to find it beautiful. The cosmic web would have exactly the same structure whether humans existed to observe it or not. But we do exist, and we do find it beautiful, and that beauty enriches our lives. It connects us to something larger than ourselves, something that existed long before us and will exist long after, something that makes us feel, paradoxically, both infinitesimally small and profoundly connected. As you drift deeper into rest, let an image of the cosmic web settle into your mind, bright filaments of galaxies weaving through space, connecting and intersecting in a pattern of stunning complexity. And between those bright threads, the dark voids, the spaces of emptiness that give the whole structure its form, light and darkness, matter and void, presence and absence, all woven together into a unified whole. It's the universe as it is, neither needing nor seeking our approval, simply existing in all its strange and austere beauty. We've spent most of our journey focusing outward, looking at the Boötes Void hundreds of millions of light-year away. But it's worth taking a moment to consider where we stand in the cosmic web. where our own place is in this grand structure of filaments and voids. The Milky Way galaxy, our home, is part of a small group of galaxies called the Local Group. This group includes perhaps 100 galaxies, with the Milky Way and Andromeda being the two largest. The entire Local Group spans roughly 10 million light-years, enormous by human standards, but modest compared to the structures we've been discussing. The Local Group, in turn, is part of the Virgo supercluster, a much larger structure containing tens of thousands of galaxies spread across roughly 110 million light-years. We're located on the outskirts of this supercluster, in a relatively sparse region between the supercluster's denser core and the voids beyond. And here's where it gets interesting. We're near a void ourselves. The local void, which we mentioned earlier, is a large underdense region about 45 million light-years from us at its closest point. It's smaller than the Boötes Void, but it's still a significant structure, and it affects our motion through space. The Milky Way and the Local Group are moving through space, not just with the expansion of the universe, but also with peculiar velocities caused by the gravity of nearby structures. We're being pulled toward the dense core of the Virgo supercluster, and toward an even more massive structure called the Great Attractor. Means our cosmic address is something like Earth, Solar System, Milky Way Galaxy, Local Group, Virgo Supercluster, on the edge between a large supercluster and a significant void. We're in a transitional region, neither in the densest parts of the cosmic web nor in the emptiest voids, but somewhere in between. This location affects our view of the universe. Because we are in a moderately dense region, we can see many nearby galaxies. The night sky, when observed through telescopes, is rich with galaxies of all types. We have access to a diverse sample of cosmic structures for study. If we were located in the centre of a void like Boötes, our observational astronomy would have developed very differently. We'd still have the cosmic microwave background, still have distant structures to observe, but the lack of nearby galaxies would have slowed our understanding. We might not have discovered galaxy rotation curves and therefore dark matter as early. We might not have seen spiral structure or interacting galaxies as clearly. Conversely, if we were in the dense core of a massive cluster, we'd be surrounded by thousands of galaxies, a rich environment for observation but also potentially problematic. The X-ray emission from hot intracluster gas might interfere with certain observations. The complex gravitational environment might make it harder to detect subtle effects. Our location seems, in retrospect, rather fortunate. We're in a place that's rich enough in structure to provide ample objects for study, but not so crowded that observation becomes difficult. It's a Goldilocks location, not too dense, not too empty, but just right for astronomy. But there's no reason to think this location was chosen or is special. We're simply here, in this particular part of the cosmic web, because this is where the matter that eventually became our solar system happened to be. The Earth formed from a molecular cloud that happened to be in this location, and that cloud formed from gas that had followed the cosmic web structure to this region. In other words, we're part of the cosmic web structure just as much as the Boötes Void is. We're embedded in filaments of dark matter, surrounded by galaxies that are all participating in the same large-scale flows of matter that created voids and superclusters. Our local environment is shaped by cosmic structure formation in exactly the same way the void's environment is. This provides another kind of connection to the void. We're not separate from it, not fundamentally different, just in a different part of the same overall pattern. The forces that created the Boötes Void also shape the region where we live. The initial density fluctuations in the early universe that made the void underdense made other regions overdense, and we happen to live in one of those denser regions. Looking out at the Boötes Void from our position in the cosmic web is a bit like looking across a landscape. We're on a hill, looking across a valley to another hill on the far side. The valley is lower, the hills are higher, but they're all part of the same landscape, shaped by the same geological processes over the same time scale. We and the void are neighbours, in a cosmic sense, parts of the same structure. And just as our position affects what we see, it also affects how we think about the universe. If we were void dwellers, we might have developed a different cosmology, one that emphasised emptiness and isolation. Being in a denser region, we developed a cosmology that emphasises structure and clustering. Both perspectives would be partially correct. Both would miss aspects of the full picture. The complete truth requires seeing the universe from all perspectives simultaneously, understanding both the dense regions and the empty ones, the filaments and the voids, the places where matter clusters and the places where it's absent. We can't literally observe from all perspectives, but we can use mathematics and imagination to construct a view that incorporates them all. And in doing so, in trying to see the universe as it truly is rather than just as it appears from our particular vantage point, we transcend our local position. We become, in a sense, cosmic citizens rather than merely terrestrial ones, people who understand their place in the grand structure and can appreciate the whole without losing sight of the parts. From here, in this quiet moment, you can hold both truths simultaneously. You're a small part of something vast, and you're also a conscious, aware part of that vastness, capable of comprehending it. You stand on a planet in a galaxy, in a supercluster, on the edge of a void in a cosmic web that stretches across the observable universe. And from that position, you can look out at the Boötes Void and understand something of what it is and what it means. That understanding is itself a kind of bridge, connecting you to the cosmos across vast distances of space and time. We've come a long way together tonight, crossing vast distances through space and time, exploring a void so enormous it challenges comprehension. We've examined it from every angle we could, its size and structure, its formation and evolution, its place in the cosmic web, its significance for our understanding of the universe. And now, as our journey draws toward its close, it's worth considering what all this means, not just scientifically, but personally. The Boötes Void is, in the end, just one small part of the universe's structure. It's large by any standard we can imagine, but it's not the largest void, not the most extreme, not unique in any fundamental way. It's simply one example of a common cosmic phenomenon, distinguished mainly by being the first large void discovered and by being well studied. And yet, contemplating it has taken us on a journey that touched on nearly every aspect of modern cosmology. The expansion of the universe, the nature of dark matter and dark energy, the formation of cosmic structure, the role of initial conditions, the power of mathematical description, the limits of our knowledge. The void has been a lens through which to view the cosmos as a whole. What started as an exploration of emptiness has revealed fullness of structure, of history, of meaning, of beauty. The void taught us that absence can be as informative as presence, that darkness has structure, that emptiness is not nothing. It reminded us that the universe is both simpler and more complex than we imagined, governed by straightforward physical laws that produce intricate patterns across unimaginable scales. Throughout this exploration, a theme has recurred: the interplay between the very large and the very small, the very old and the very new, the known and the unknown. The void formed from tiny quantum fluctuations in the early universe, and grew to become one of the largest structures we know. Its present state was determined billions of years ago, and its future will unfold over billions more years. We know much about it, yet mysteries remain. There's a kind of peace that can come from contemplating these cosmic truths. Not the peace of having all questions answered, but the peace of accepting our place in a vast, ancient, ongoing process. We're temporary, yes, but we're part of something that isn't temporary. Our individual lives are brief, but the matter we're made from is ancient, and the patterns we participate in are cosmic in scale. The void doesn't care about human concerns, doesn't respond to our hopes or fears, doesn't change based on what we think about it. It simply exists, evolving according to the laws of physics, indifferent to observation. And there's something clarifying about that indifference, something that can help put our own concerns in perspective. The problems we face in life don't become less real when set against cosmic scales. The joys don't become less joyful, the sorrows less sorrowful. But perhaps they become less overwhelming, less all-consuming. When you know that the universe contains structures like the Boötes Void, that existence operates on scales both vastly larger and vastly smaller than human experience, it becomes easier to hold your own experiences lightly. This isn't about diminishing human life or suggesting that cosmic perspective makes our concerns meaningless. Rather, it's about finding balance, about recognizing that we're part of something much larger than ourselves, without losing sight of our own significance. We matter because we're conscious, because we're capable of understanding, because we can appreciate beauty and seek truth and create meaning. The void, for all its vastness, cannot do any of those things. It has no awareness, no curiosity, no capacity for wonder. We do, and that makes us, in a sense, more remarkable than the void, despite being so much smaller. Size isn't everything. Consciousness counts for something. So as we prepare to end our journey, let yourself feel both small and significant. You're a tiny speck in a vast cosmos, yes, but you're also a part of the cosmos that's capable of knowing itself. You're made of atoms that have journeyed through voids and stars, across billions of years and billions of light years. You carry within you the history of the universe, and you carry forward its capacity for awareness and understanding. The Boötes Void will continue to exist long after you and I are gone, long after human civilization has ended, perhaps long after the sun has exhausted its fuel and the earth has become cold and dark. It will expand slowly, its few galaxies drifting farther apart until eventually in the far future it might become representative of the universe as a whole, vast, empty, dark and cold. But that's then. Now we live in a universe still rich with structure, still full of galaxies and stars, still young enough to harbour life and consciousness. We live at a time when voids and filaments coexist, when the cosmic web is clearly visible, when structure and emptiness balance each other in a pattern of extraordinary beauty. We're fortunate to exist in such a time, in such a place, with the ability to observe and understand the cosmos. We're fortunate to have discovered the Boötes Void, to have mapped its extent, to have pondered its meaning. These are gifts, not given by any giver, but simply present in the nature of reality, available to those who look carefully and think deeply. And so, as you drift towards sleep, let the void drift with you in your awareness, not as something frightening or disturbing, but as something peaceful and profound. Let it remind you of the universe's vastness, of your small but meaningful place within it, of the ancient dance of matter and energy that brought you into being and connects you to everything else that exists. The darkness of the void is not the darkness of annihilation, but the darkness of possibility, the space from which new things can emerge, the quiet from which new songs can be composed. Rest in that darkness. Let it hold you gently. And know that you're part of something vast and ancient and beautiful, something that includes both the bright galaxies and the empty voids, both the presence and the absence, both the known and the unknown. The Boötes Void is out there, hundreds of millions of light years away, expanding slowly into the cosmic night. And you are here, consciousness arising from matter, awareness emerging from atoms, understanding growing from curiosity. Both are part of the universe's. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. Both are part of the universe's story. Both are necessary. Both are, in their different ways, beautiful. And in recognizing that, perhaps we find a peace deeper than any particular knowledge. A calm that comes from accepting our place in the grand cosmic pattern and finding that place good. We've travelled together for more than 2 hours now, drifting slowly through the vast emptiness of the Boötes Void, exploring its boundaries and its history, its significance and its mystery. Thank you for staying with me through this entire journey, for giving your time and attention to this exploration of cosmic darkness. It's been, I hope, a gentle voyage that's left you more relaxed than when we began, more connected to the universe than you might have felt before. From the discovery of the void by Robert Kirshner's team in the late 1970s, through our understanding of how it formed from tiny density fluctuations in the early universe, to our contemplation of what it means for our place in the cosmic web, we've covered enormous ground. We've examined the physics of absence, the mathematics of emptiness, the beauty and structure, and the peace that can come from cosmic perspective. At the beginning of our journey, I posed an implicit question. How does something this large, this empty, come to exist in a universe that's supposed to be expanding uniformly? The answer, as honestly as I can give it, is this. The universe was never perfectly uniform. Tiny variations in density existed from the earliest moments, and those variations, amplified by gravity over billions of years, created the cosmic web we see today. The Boötes Void is one expression of that web, a region where matter flowed away rather than clustering together, shaped by the same forces that created the galaxies we can see. Perhaps the deeper answer is that the universe needs both fullness and emptiness, both structure and void, to be what it is. The cosmic web could not exist without voids to give the filaments their shape. The beauty of cosmic structure comes precisely from the interplay of light and darkness, of presence and absence. The void is not a flaw or a failure, but an essential part of the pattern. If you enjoyed this slow drift through cosmic darkness, a like and subscribe really helps this channel reach others seeking the same peaceful way to end their day. And if this exploration resonated with you, I'd love to hear your thoughts in the comments. Where in the world are you watching from? What draws you to these cosmic topics? What would you like to explore next? To those already subscribed, thank you for being part of this community, for choosing to learn as you fall asleep, for trusting me with your nights. Your presence here, quiet though it may be, matters. Together, we're a community of cosmic explorers, finding peace and wonder in the universe's vastness. Wherever you are in the world right now, whatever darkness surrounds you, I hope you found comfort in this exploration. I hope your breathing has slowed, that your thoughts have quieted, that your body feels heavy and warm and ready for sleep. I hope the day's concerns have faded into the background, replaced by a sense of connection to something larger and older, and more enduring than any single day's troubles. Look up at the night sky, if you can. Either now or tomorrow night, even if you can't see it, imagine it. All those stars, all those galaxies arranged in the cosmic web's magnificent pattern. And somewhere out there, in the direction of the constellation Boötes, a vast darkness, a void containing few galaxies but infinite space, expanding slowly as the universe ages. All those photons that left the void hundreds of millions of years ago, travelling through expanding space, finally arriving at Earth, where some of them entered telescopes and revealed the void's existence to us. All that distance crossed, all that time elapsed, so that we could know about this emptiness and find meaning in it. Perhaps there's something beautiful in that improbable chain of events, the formation of the void, the evolution of life on Earth, the development of human consciousness and curiosity, the invention of telescopes and spectroscopy, the patient work of astronomers, and finally you hearing about it tonight as you drift towards sleep. All of cosmic history led to this moment, to this quiet awareness of a vast darkness billions of light years away. Sleep well, knowing you're part of this grand cosmic story. Dream of vast dark spaces between galaxies, of matter flowing along invisible threads, of structures emerging from chaos, of consciousness arising from matter. Dream of the cosmic web in all its strange beauty, and of your place within it, small but meaningful, temporary but connected to the eternal. The universe is vast and you are small. But you are also the universe's way of knowing itself, and that is not small at all. You are consciousness, awareness, understanding, emerging from matter that has travelled through voids and stars across billions of years. You are stardust contemplating darkness, atoms observing emptiness, the cosmos exploring itself through human eyes and human minds. Rest now. Let the void's vast darkness hold you gently. Let the cosmos's ancient rhythms lull you towards sleep. Let your awareness drift, like a galaxy in a void, peaceful and alone, but part of something larger. There is nowhere you need to be, nothing you need to do. Just rest and dream and know that you are held by the same forces that shape galaxies and voids, that you are as much a part of the universe as any star or void or cosmic web. Good night. May your dreams be peaceful, filled with stars if you wish, or with darkness, or with whatever brings you rest. May you wake tomorrow refreshed and renewed, carrying with you some echo of tonight's journey, some sense of connection to the cosmos. May you look at the night sky with new eyes, knowing something of what lies beyond the stars you see. The Boötes Void is out there, waiting in patient darkness, and will be waiting still when you wake, when you grow old, when generations pass. It is a permanent feature of our universe, a vast emptiness that teaches us about presence and absence, about structure and chaos, about the patterns that emerge when simple laws operate over cosmic time. And you are here, now, consciousness arising briefly from matter before returning to it, aware for a little while of the vast cosmos in which you exist. What a gift that awareness is. What a strange and beautiful universe we inhabit. What a privilege to explore it together, even if only through words and imagination, even if only for a few hours on a quiet night. Good night, traveller through cosmic darkness. Sleep well, dreamer of voids and galaxies. Rest peacefully, knowing you are part of something vast and ancient and ongoing. The universe holds you gently. The darkness is not empty but full of possibility. And tomorrow, when you wake, the cosmos will still be there, waiting to be explored anew. Good night.